Good afternoon, dear students. So, how are you all? Hmm?
Fine, sir.
Good afternoon, sir.
Good
Well,
afternoon, sir.
good afternoon.
Fine, sir.
Yeah,
Fine, sir.
hmm, good. So, we are about to finish the second actually module. That is okay. Nohosal, his network is not that good. He's saying, okay, I will be uploading this video lecture. Okay, then in the Google Classroom, then you can have a look from there. Okay, Nohosal. So yes, so we are about to finish this second law of thermodynamics. Then we will be going to our third module, that is entropy. Okay, so as because this semester, I think all of you are aware that your first class test will be held on in the month of December. Okay, instead of this November. So we will get another 3 4 cycles to complete the syllabus, and which I think it is good for all of you. Okay, so today there's just one topic. Okay, it is left. It is actually we need 2 class to complete this topic. Let's see whether we can complete in this hour or not. If it is not completed, then we will be completing it in the next hour. Okay, means we will be having another class now at 3:35. So let's see whether it is completed or not. So till now you have come to know actually what is the first law of thermodynamics, and what is the second law of thermodynamics, isn't it? So what is the first law of thermodynamics? That is, in a cyclic process, the summation of, oh, my voice is breaking. uh, is it breaking for others? Rishikesh, Teja?
Mm, No, sir.
No, sir.
Oh, might be
No,
they
sir.
might be having some network issue. Okay, no problem. If it is breaking, you can watch it later also, but just present. Okay, be here in this class. Yeah. So the first law of thermodynamics, it states that in a cyclic process, thermodynamic process, the summation of net work and net heat, it is equal, isn't it? Summation of heat equals to summation of work in a cyclic process. Okay, and uh, if we just analyze, or if we just explain that same concept for a process, so our equation, okay, of this first law of thermodynamics was what was the actually equation, or what was the formula to represent the first law of thermodynamics for a process? It is Q equals to delta U plus W, isn't it? So means the heat, it is not 100% converted to work. Okay, so some part of the heat, it is utilized in increasing the internal energy of the system, and that internal energy, it is denoted by delta U, change in internal energy. Okay, so this concept, it is applied to a heat engine. Okay, in the second law of thermodynamics, this concept, it is applied to a heat engine, and finally we see that the heat engine can produce work when it operates in between two temperature. That is, this heat engine which will be working in a cycle. Okay, cycle means the initial state will be equal to the final state. Okay, and how this initial state, it equals to the final states, we have seen. Okay, so we have introduced some of the components, just like evaporator, then pump, okay, then your heat exchanger, okay, or expander, then again turbine, again back to the pump. Okay, so it is a cyclic process. Okay, so this component, this circular component, basically it represents that that diagram, okay, which we have already seen in refrigerator or in heat pump. Okay, so this actually here it is shown by a circular diagram. That is, it is a heat engine. So when, how a heat engine can produce work? So when it will operate, okay, in between two constant temperature source. So here it is constant temperature, having constant temperature T1, okay, so which will be supplying heat Q1. Okay, and it is producing some work, so which is lower than this amount of heat, because all the quantity of heat it is not converted to work. So some part of the heat it will be rejected to the sink. Okay, means what? The heat engine will be producing some work when it will be operating in between two constant temperature source. Okay, so this is one source and this is another source, that is called a sink. So the engine where it is rejecting heat, it is called as the sink. Understood? Okay, so what is a heat engine? If I will ask you what is a heat engine, what is a engine? So a engine or a heat engine will be an engine which will take heat. Okay, heat engine. So which will take heat and it will do some mechanical work, W. Okay, so here it is taking heat and it is doing some mechanical work. Okay, so just like your motor vehicle engine, your Maruti car engine, okay, your Honda engine, so it is taking heat in terms of what? Fuel. So your petrol, it is burned inside the piston cylinder and the engine is producing some power, and due to that power the tire rotates, isn't it? The wheel rotates. So because of the application of the heat, okay, Q1, so which is taken from the petrol, okay, so it is doing some work W, okay, which can be felt or which can be seen in the tires, in the wheels. At the same time the engine is also getting heated, isn't it? So that amount of heating is due to this Q2, because this, in a cyclic process, the engine will exhaust, okay, the engine will dissipate some heat to the outwards, okay, to the surrounding, and this is the amount of heat. Understood? So when heat is taking by the engine, so it will be doing some work, and at the same time it will have to release the heat to some other component, otherwise it cannot produce this work. So it happens for every engine. Okay, your diesel generator, okay, which will produce electricity when the current electricity, okay, it is not there, when the electric supply is not there. So your motor vehicle engine, okay, all those engines are cyclic heat engine. Understood? So this is the basic principle. Okay, so Kelvin, Planck and Clausius, so they give two different statements, but you can prove that if you violate one statement, then the other statement also violates. Okay, means they are equivalent concepts. These two are the equivalent concepts of second law of thermodynamics. So all these engines, okay, so basically run by some principle. Okay, so what is a cycle actually? Here you are saying that cyclic heat engine. So cyclic heat engine, it does not mean that in a circular way the cycle will happen, but it should, the initial state should be equal to the final states. Okay, so it may be a rectangular form also, it may be a trapezoidal form also, but what in the diagram it should indicate that the initial point and the final point should be same. Okay, yes. So all this engine basically works on the basis of some uh, theoretical cycle. Okay, so today we will going to see what is that cycle, okay, with respect to these all these engines basically runs. Okay, so one very famous scientist, Sedi Carnot, so he developed a very hypothetical concept. Okay, so he developed a hypothetical engine, so practically which is not possible. So on the basis of that engine, so all the cycles are basically developed. Okay, so the principle by which your motor vehicle runs, so it is basically on the basis of this Carnot engine. So this Carnot engine, it is a hypothetical engine. Okay, so it is a theoretical engine and it is a reversible heat engine. What is a reversible process? Suppose one thermodynamic process happens from state 1 to state 2. Okay, so in a PV diagram, PV plot, so from state 1 to state 2, one process is happening. So if you just reverse this process, if you go from state 2 to state 1, so if all the properties, okay, of the system and the surrounding remains the same. Okay, so at the beginning, whatever the states of one, the properties, if going back from 2 to 1, if all the properties are same, then it is called as a reversible process. Okay, and I told you that the reversible process can be shown by what? Distinct lines. Okay, by distinct lines. And irreversible processes are shown by dotted lines. Understood? Just wait. Yeah. So it is a reversible heat engine, means all the processes which will be happening inside that engine can be reversed. Okay, means if for from process 1 to 2, if you just draw the process, if you are able to draw the process, or if you attain this process, so from 2 to 1, if you go by a reverse direction, so you will attain the same initial condition for the system and the surrounding. Okay, so it is a hypothetical engine, that is why it is a reversible heat engine. Okay, and it is the most efficient engine, as because this is a theoretical engine, so its efficiency is taken to be maximum. Okay, so it is not 100%, but its efficiency will be maximum efficiency. So whatever engines those will be built, okay, in the universe practically, so those efficiencies will be always lower than this Carnot engine efficiency. Okay, so it is the most efficient engine. So these are the actually assumptions. Okay, so this Carnot engine uses ideal gas as the working fluid. Okay, so in petrol engine, so petrol it is used, in diesel engine, diesel it is used, but here the Carnot engine, it uses ideal gas. Okay, it will obey the ideal gas laws. Understood? So now we will see what is actually a Carnot engine. Okay, as I have told you, so it is a hypothetical engine. So basically, what are the components those comes to your mind when we say an engine? So when we will say an engine, there will be piston. Okay, this is the piston. Okay, and one cylinder will be there, because in our automobile engine there is a piston, there is a cylinder. Okay, so in our bikes it will be a single cylinder engine. So in 1000 cc motor car, so there may be three cylinders. Okay, so in 1400 for 1400 cubic centimeter car, there may be four cylinders, okay, inside the engine. So here we have taken one engine, okay, one cylinder, one piston arrangement. Okay, so inside which some ideal gas will be there. Understood? So this is one engine. So this engine needs to operate in a cyclic way. Okay, then only we will get a Carnot cycle. So what is a Carnot cycle? We will see. Okay, what are the basic processes those are involved in the Carnot cycle? So here it is the idealized thermodynamic cycle consisting of four reversible processes. Okay, so a Carnot cycle will be completed by four reversible processes, because whatever processes will be happening in the Carnot cycle will be a reversible process. As I have told you, what is a reversible process? That the change of state, okay, can be achieved, means from 1 to 2 if states are changing, and if you go from in a reverse direction, you can attain the initial state. Okay, all the properties will be same. Okay, provided each of the point in that process should be a thermodynamic equilibrium process, and that process should happen very slowly. Okay, very quasi statically, very slowly, then only each of the points in a process will be having equilibrium points. Okay, so that thing we have discussed in the thermodynamic equilibrium. Okay, so in a Carnot cycle engine or Carnot heat engine, there are four cycles. Okay, so the first cycle is reversible isothermal expansion. Okay, so what is an isothermal process? So a process where there is a constant temperature. Okay, there may be change in pressure, there may be change in volume, but there the temperature should be constant. So that process is called as isothermal process. Okay, so first process is in the Carnot cycle or Carnot heat engine is the reversible isothermal expansion. Okay, means temperature will be constant but expansion will happen. So when there will be an expansion, so there will be an increase in volume. Understood? There will be an increase in volume and increase in what? Decrease in pressure. Okay, so the first process will be reversible isothermal expansion. Understood? Just you need to remember all these four processes. Then reversible adiabatic expansion. So what is an adiabatic process? So adiabatic process is a process where the system is insulated. Okay, so the system is insulated and no heat transfer occurs in between the system and the surrounding. Understood? So temperature may fall, temperature, there may be change in temperature. Okay, so here it is written that th means hot, th means hot. Okay, means higher temperature turns to lower temperature, but there will not be any change of heat in adiabatic process. Okay, so there will not be any means transfer of heat within the system and the between the system and the surrounding. The third one is the reversible isothermal compression. Okay, so isothermal means what? Temperature will be constant but compression will happen. Means if you compress one system but the temperature, okay, should be constant for the system. Okay, so it is basically theoretically it is not, practically it is not possible, isn't it? Because when you are compressing something, the intermolecular forces will increase, isn't it? Molecules will collide and it will increase the temperature of the system, isn't it? So it will only happen when that isothermal process will be very slow. If you just feel it physically also, so if you are compressing, so if you just imagine your two hands and if you want to compress it, okay, so what will happen? So you can feel that the temperature will increase because the collision between the molecules inside the system will increase, isn't it? So if that process happens very slowly, the collision, okay, it will be uniform. Okay, so there will not be any increase in temperature theoretically. Okay, so basically this isothermal process happens very slowly. Okay, and this adiabatic process happens very fast because there should not be any change in there should not be any interaction of heat. Okay, so if there should not be any interaction of heat, the process should be very fast. Okay, instantly that process should happen. Okay, then only these adiabatic processes are possible. Okay, the third one is reversible isothermal compression and fourth one is reversible adiabatic compression. Just the reverse of these two processes: reversible isothermal expansion, here it is reversible isothermal compression, and here it is reversible adiabatic expansion, and here it is reversible adiabatic compression. So what will happen to this system under these four processes? So we will see, all these parameters are written here, but we will see in a graphical form. Okay, so in two steps we will see. So here it is the cylinder. Okay, this is a 2D view, so you can imagine it in 3D also. So this will be a cylindrical cylinder, and this is a piston where ideal gas is there. Okay, so here from a hot reservoir, okay, hot reservoir, so in automobile engine this is happening by burning the fuel. Okay, so here is a hot reservoir. Okay, so this, from this hot reservoir, this q2 amount of heat, okay, it will enter to the system. Okay, but temperature of this cylinder, it is constant. So is it possible when heat is coming inside and temperature remain constant? So it is not possible. It is only possible when this process happens very slowly, as because this is a hypothetical cycle. Okay, hypothetical process, that is why the heat enters very slowly. Okay, very slowly. So infinitesimal temperature difference, okay, temperature gradient will be there. So very slowly heat will enter and it will not raise the temperature of the system, but the piston will expand. Okay, the piston will move upside. Okay, means there will be the change in volume, increase in volume. So volume will increase and the temperature will be remain constant for this reversible isothermal expansion. Okay, so this is the first process, reversible isothermal expansion. So here it is 1 to 2. Okay, so from state 1, so state 2 happens. Okay, so P1 V1 changes to P2 V2 because pressure will decrease and volume will increase, isn't it? So earlier if it is P1 V1, now it is P2 V2, but temperature is remain same, TH. If it is TH, then it is in the second state it is TH. Okay, because it is isothermal. Now the same cylinder piston, now it is just it is placed, okay, on an insulated stand. Means earlier it is metallic stand, okay, diathermic stand, so heat can enter. Now it is insulated, okay. So if it is insulated, so what will happen? There will not be any interaction of heat from the surrounding to the system or from the system to the surrounding. Understood? But what will happen? So due to the internal energy, okay, due to the internal energy, change in internal energy, the piston will again, okay, try to expand, okay, but temperature will be lowered because there is no change in what? Heat, okay. There is no exchange of heat, but there is a expansion, okay. So as because there is an expansion due to this intermolecular energy, okay, internal energy, so the temperature will fall, okay. So it will fall from TH to TL, or you can say if it is T2 it is T1, okay. So the temperature will fall to T1. Understood? Now the same, it is the forward process, okay, it is the forward process, and these are two are the reverse process. Means these are the expansion process, these are the compression process. So reversible isothermal compression. So now what will happen? So this heat which is available here, okay, so it should be rejected, otherwise the system will not be able to produce work, isn't it? Because we also know that by the second law of thermodynamics, then actually for a engine, so we need output, isn't it? We need work. So it is only possible when it will reject heat, okay, to some sink. Now one sink it is attached, and this insulation it is removed, okay, this stand is removed, and now it is connected to metallic wall, okay. So what will happen? The heat will be moved out, but at constant temperature. So is it possible practically? So practically it is not possible, but theoretically it is possible when the process is happening very slowly, okay. So when this process is happening very slowly, so this is called as isothermal, and it is compressing, means volume is getting reduced, pressure is increasing, okay, temperature remain constant, and heat is going out, okay, to the sink, okay. So now the fourth process is reversible adiabatic compression, okay. So now the internal energy is increased for this system. Now what will happen? So we need to just remove, means balance the system. That is why we will be introducing it to this insulating stand, so where there will not be any exchange of heat, okay. So in these two diagrams there are no exchange of heat, okay, but temperature will increase, isn't it? Because of this internal energy, okay, as because there is a compression, there will be a huge intermolecular energy, internal energy, and this will rise the temperature, okay. Means initially our temperature was TH, okay, and in the intermediate states it falls to TL. Means you can say this is T2, this you can say this is T1, okay. From TH to TL it falls, and again it gains the initial conditions, okay. Again it gains the initial condition, TH temperature. Means it is a cyclic process, okay. So one cyclic process it is completed, and the system will be generating some work. So how much work it will generate, so we will see, okay. So I think till now you are getting what I am saying. Rishikesh, Nath, Rehan,
Yes, sir.
Yes, sir.
are you getting what I am saying? समझ में आ रहा है रेहान?
हाँ सर.
Nilutpal?
Sir, sir, one question, sir.
Yeah.
Sir, this type of process in the Carnot, basically, it is found in the IC engine, or it was something different?
See, I am not saying that exactly this Carnot cycle you will get in IC engine. Okay, so IC engines are basically auto cycle engine and diesel cycle engine, but this is the basis of all these cycles. Are you getting what I'm saying? Because this is
Yes,
the
sir.
heat engine. Those are specific engines. Okay, so you should know the principle of the basic engine. After that, you can categorize all the other engines. How a petrol engine will run, how a diesel engine will run. All those things will come. Auto cycle, diesel cycle, all will come. But this
Okay.
was the first cycle, hypothetical cycle, which was made in the 18th century by Carnot. Okay, and which is having the maximum efficiency. Okay, but theoretical. It is theoretical, not in practical. Okay, but all these
Okay,
auto
sir.
cycle, diesel cycles all are practical engines, because we need practical motor cars, isn't it? All the cars are
Yes,
running
sir.
on the road. So all these cycles are categorized after on the basis of this Carnot cycle. Okay, so we will come to
Okay,
all
sir.
those things in the fifth module. Okay, just this is the
Okay, sir.
basic one. Okay, yeah.
Okay. Okay, sir. Okay.
Yes, anyone having any question? Partha, Farmiki,
No, sir.
Partha. Okay, okay, yeah. Let's move then. Okay, so these four processes, basically these are these four processes. Okay, now we will see how these processes will look in a graphical way. Okay, what is the graphical representation? Very simple. Okay, very simple. So this is a PV plot. So PV diagram of the Carnot cycle. Okay, PV plot. So in PV plot, so from where we have started, so from one we have started. Okay, how we have started? First process was the isothermal, reversible, though it is reversible, all the processes are reversible, that is why I will not say reversible. So it should be taken into granted that all the processes are reversible. So from 1 to 2 it is one process. So it is a isothermal process, and for isothermal process means temperature is constant and it happens very slowly. Okay, so it was happening very slowly in the piston cylinder arrangement. Okay, I am not showing you the previous slide, I think it is already remembered. Okay, so this one, so for this 1 to 2, so this graph, okay, this type of graph, inclined graph, not straight line, it is a little bit curvy, so this will show an isothermal curve. Okay, so from 1 to 2 it is isothermal process. Okay, so in PV diagram this is the notation of isothermal process. Okay, one curvy line. Okay, in this way. So 1 to 2 is an isothermal process. What happens in that isothermal process? So QH heat, it is entering to the system. Okay, so in our previous diagram, so QH heat was entering to the system. That is why this QH heat is shown. Okay, from 1 to 2. So TH is constant because isothermal. Now from 2 to 3, it is adiabatic expansion. Okay, so in adiabatic expansion, there will not be any exchange of heat, but there will be change in temperature inside the system due to internal energy. Okay, so the temperature will be lowered. Okay, because there is no external heat source, so temperature will be lowered. Okay, so volume will expand in both the cases. In this process also volume will expand, in this process volume is expand. If you just project this point here, so this one point, this is V1, so V2, so here it is having greater value, and at V3 it is also having greater value, means up to this much. Okay, V3 the piston will expand. Understood? And this is the forward process, isothermal process, adiabatic process, means isothermal expansion, adiabatic expansion. Now from 3 to 4, this process is called as isothermal compression process. Okay, so this process will happen very slowly, and in this process there will be a rejection of heat. Okay, so in this process there will be a rejection of heat to the sink or to the surrounding. Okay, so here in the rejection of heat, the temperature is constant. That is why this line and this line, you can see that these two lines look similar, not lines, these curve paths look similar, isn't it? So TL constant because this is isothermal, and it will happen very slowly. Okay, practically it is not possible, but theoretically it is possible that uh, you have to manage the temperature constant, and at the same time you need to release the heat from the system. Okay, so why the system is taking heat and releasing heat? Because in a cyclic process, if a engine, okay, if an engine needs to produce some work, it should operate in between two constant temperature source, otherwise it cannot produce work. Okay, if it is taking heat, at the same time it should release some heat, otherwise it cannot just produce work, just like your automobile engine. Okay, so from petrol it is getting the heat. Okay, and it is producing the work, and at the same time the engine is getting heated. Okay, so that much heat it is releasing. So this is isothermal compression, 3 to 4, and then 4 to 1, the uh, metallic insulation it is removed, or metallic plate it is removed, and the insulation it is given. Okay, no heat interaction between the system and the surrounding, and the system will comes to the initial, okay, initial condition. So from TL, the temperature will rise because this is a compression, okay, due to the internal energy, the temperature will rise from TL to TH, okay, or you can say that T1 to T2, the temperature will rise. Understood? So this is a complete Carnot cycle in a PV diagram. Understood? So this is the forward part, okay, and this is the backward part. Here the arrow marks are not shown, but better you should show the arrow mark. And this is the basic drawing, okay, this is the basic graphical representation of this Carnot cycle. Understood? So up to this much, I think the point is clear to you, the concept is clear to you. Okay.
Yes, sir.
Okay, okay, very simple,
Sir.
very simple.
Yes, sir.
These four sites, okay, you can say that curvy sites will represent all these four processes of a Carnot cycle. 1 to 2, the reversible isothermal expansion. 2 to 3, the adiabatic expansion. 3 to 4, the isothermal compression. 4 to 1, the adiabatic compression. Okay, so the cycle it is completed. Okay, so I have told you earlier that cycle doesn't mean it should be a circular path. Okay, the state should be same, the initial state and the final state should be same. Okay, yeah. So now we will be calculating the efficiency. Okay, so just skip these 3 points, 1, 2 and this one. Just go to this one, thermal efficiency. So in heat pump, in heat engine, we have seen the efficiency. So what is our, yes, I think someone is, yeah, Nilutpal, please mute yourself. Nilutpal. Okay, yeah. Okay, so thermal efficiency is what? So for an automobile, what should be our efficiency? Our output divided by input. So what should be our output? So our tires or wheels should rotate, isn't it? Means some power should generate. So which is the parameter which is related to power? That is the work. Okay, so work upon the heat which is taken from the petrol. Okay, so that is, or diesel or fuel. So that is the input, isn't it? So net work divided by heat input is the efficiency for a heat engine. Okay, so thermal efficiency for a Carnot cycle will be W net. Okay, net work output divided by QH, means this was the heat which was taken by the system initially. Okay, because we are supplying this amount of heat and the system should do this amount of work. Okay, so then the thermal efficiency of the system will be W net upon this QH, and this is nothing but, W net is nothing but Q1 minus Q2, or QH minus QL. Okay, already we have seen this one, because in the first diagram you have seen Q1 minus Q2 is W net. Okay, so if it is QH, if it is QL, so QH minus QL, okay, divided by QH will be the efficiency for this system. Understood? So very easy. Okay, so this can be converted to 1 minus QL upon QH. Okay, and this QL by QH can be replaced by TL by TH, so which I will prove, okay, in this class. So in the next slide, so we will show that this thermal efficiency of this Carnot cycle is 1 minus QL upon QH is equals to 1 minus TL upon TH. So how you can replace this QL by QH by TL by TH? So I will prove now. Okay, so this relationship is often called the Carnot efficiency, since it is usually defined in terms of Carnot heat engine. Okay, so this is the Carnot efficiency. So if you are asked theoretically, okay, so in some viva, so what is the Carnot efficiency? It is this one. Okay, either this one expression or this one expression you can say. Okay, and you may be asked whether a Carnot engine is having 100% efficiency or not. Yes, this Carnot engine, it is no, actually it cannot have 100% efficiency. Okay, so in physics, I think all of you have read that an ideal engine, Carnot engine, can have 100% efficiency, but in this mechanical engineering, okay, an ideal Carnot cycle, it cannot have 100% efficiency because of this PMM2 machine. Okay, perpetual motion machine of second kind. I have told you about that concept, okay, in the equivalence of Kelvin, Planck and Clausius statement. Okay, so now we are going to prove this one, that instead of this, how we can write this one. Okay, so this QL, yeah, L can be replaced by 1 and H can be replaced by 2. Okay, if you just using those suffixes, because previously we were using those suffixes. Now we will see. Okay, so this is the Carnot cycle. So in PV plot, I have just drawn this one. So what is our initial pressure? Let's say it is P1, P1, T1. Okay, so this is an what? Isothermal process. So the pressure will change, the volume will change, volume will increase, isn't it? So here if you just project it, the volume will increase in this axis. Okay, and pressure, so it is dropping. Okay, so pressure, it is dropped, decreased. So P2, V2, but here it is T1 because the temperature is constant. This is isothermal curve. Now it is adiabatic. Okay, so in adiabatic expansion, as because it is expansion means what? Volume is increased. So from V2 it is V3. Okay, so volume is increased and pressure again drops to P3 and temperature drops to T2. Okay, so earlier there it was they have written as TH and TL. I have written as T1 and T2. Here it is T1 greater than T2. Okay, you need to take that T1 greater than T2, just like TH greater than TL. Okay, so P3, V3, T2. Okay, temperature is changed. Now here this is again isothermal process, so temperature will be constant. So as because this is T2, so this will be also T2. Okay, so here it is P4, P4. Okay, so in this isothermal expansion, this one first process, I have marked it with AB process. So what is the change in temperature? So it is 0. Okay, what is the change in internal energy? As because the internal energy is a function of temperature, so as because the temperature is 0, change in temperature is 0, the internal energy change is also 0. Okay, this is not V, this is U. Okay, U1, this is U1, delta U1. So if you just apply the first law of thermodynamics for this process, so what will the expression? So Q1 will be equals to what? W1 plus delta U. So this is the expression of first law for a process, isn't it? So here delta U equals to 0. So Q will be equals to W, means W1. So for this process, let's say it is W1. So W1 will be equals to what? So for a isothermal process, so what was the work done? I have given you this one, okay, in a PDF file, and we completed this topic in our class. So what is the work done for an isothermal process? So nRT1 logarithm log base E V2 upon V1, so which is equals to Q1 because Q equals to W. Okay, so this was proved in the earlier classes in the first law of thermodynamics. Okay, so nRT1 log base E V2 upon V1. Okay, so this is isothermal expansion work done. Now for BC, so B2C for this adiabatic expansion, so what is Q? So as because this is adiabatic, so there will not be any change in heat, okay, in between the system and the surrounding. So Q will be equals to 0. Understood? So what will be W2 then? So for an adiabatic process, the work done is given by NR T2 minus T1 1 minus gamma, because there is an expansion, okay, by the system. So that expansion is nothing but the work done by the system. Okay, positive work done by the system. This one also positive, this one also positive. NR T2 minus T1 1 minus gamma. Okay, then what will be Q? So Q is 0. For this process, you can apply the first law of thermodynamics. Q equals to W2 plus delta U2. Okay, so this Q equals to 0. So delta U2 means change in internal energy will be equals to minus W2. So minus of NR T2 minus T1 1 minus gamma. So minus sign I have written. So for CD, again it is a isothermal process, delta U3 0. Why it will be 0? Because the change in temperature is 0. As because internal energy depends on the temperature, that is why this term will be 0. So Q2 will be W3. Okay, so what will be the value? So for isothermal process, the change in this one, the work done is given by this one. Okay, nRT2 log base E V4 by V3, just like this one. Okay, the final volume divided by the initial volume. So here it is V3, here it is V4. Okay, again for this adiabatic compression from D to A, so what is happening? There will not be any change in heat. Okay, so Q will be equals to 0, so W4 will be equals to nr T1 minus T2 1 minus gamma. Okay, so delta U4 will be equals to, so this one. Okay, because this will be negative, so if you just put it in just like this one, uh, W delta U2 equals to minus W, so just like delta U4 it will be minus W. Okay, W4, so this value is this one. Okay, so now you can see the feasibility of this cycle. Okay, so first you see the change in internal energy for the whole process. Okay, for this whole cycle, here it is 0, here to here the change in internal energy is 0. Okay, and for this process also, this isothermal process also, the change of internal energy is 0. Only in this adiabatic process, adiabatic expansion, and in adiabatic compression, there are values of delta U2 and delta U4. Now you see here it is nr T2 minus T1 1 minus gamma, and here you can see nr T1 minus T2 1 minus gamma, just the reverse. So if you just add these two, okay, delta U2 plus delta U4, so it will be cancelled out. Means what? So here also in the whole cycle, the change of internal energy it is 0. That means your analysis is it is correct. Okay, because for a complete cycle, for a cyclic process, the change of internal energy is 0. I have written in a cyclic process the change of internal energy is 0, and from mathematically also you can prove that the change in internal energy is 0 if you just add delta U1 delta U2 delta U3 delta U4, so you will get 0 value. Understood? Now what will be the work done? Okay, so here work done, you need to count W1 W2 W3 W4, because you need to calculate the efficiency. And what will be the efficiency? Net work divided by the heat input, isn't it? So what will be the net work done? So if you just want to calculate the net work done, so here the work done was this one. Okay, in the second process the work done was this one, in the third process the work done was this one, and in the fourth process the work done was this one. This one and this one, it will be cancelled out, because T2 minus T1, here also T1 minus T2, just if you just add these two work done, so it will be cancelled out. Means in adiabatic expansion and adiabatic compression, these two work done will be cancelled out. Okay, so now only the net work output will be the addition of this work. Okay, isothermal expansion work and isothermal compression work. So nRT1 log of V2 by V1 plus nRT2 log of V4 by V3. Okay, so efficiency is W net upon Q1. Okay, so Q1 is basically what? W1, because it is proved Q1 equals to W1 is because the internal energy was 0. So instead of this W1 or instead of this Q1, you can write this one. So we have written this one. Okay, so NR, it is common to all these three terms. So NR will be cancelled out. Then if you just divide it T1 log V2 by V1, T1 log V2 by V1, only 1 you will get, plus T2 by T1, okay, log V4 by V3 log base E V2 by V1. So this efficiency you will get. Now according to the gas law, what you can write as, because this is ideal gas. Okay, here the working fluid is what? Ideal gas. So you can use the ideal gas laws. Okay, so P1 V1 equals to P2 V2, because this is an isothermal process. So for isothermal process, okay, according to Boyle's law, you can write P1 V1 equals to P2 V2. For adiabatic process, you can write P2 V2 to the power gamma, P3 V3 to the power gamma. Okay, so for CD, what you can write? P3 V3 equals to P4 V4, because this is isothermal process. Okay, isothermal process. And for this adiabatic process, so P4 V4 to the power gamma equals to P1 V1 to the power gamma. Okay, so this already we have studied in the first law of thermodynamics. Understood? So give it equation number 1, 2, 3, 4, and you multiply all these 4 equations. So what you will get? So P1 P2 to the power gamma, okay, P3 to the power gamma. So P1, all these term will be cancelled out. P1, okay, all these term will be cancelled out, because these are left hand side term, these are right hand side term. So only V, okay, terms will be there. So V1 V2 to the power gamma, V3 V4 to the power gamma, P2 V3 to the power gamma, V4 V1 to the power gamma. Okay, so if you just arrange this, so what you will get finally? So V2 by V1 will be equals to V3 by V4. Okay, so this one you will get this ratio. So if you put this ratio here, so one thing you need to actually see very minutely, that here it is V4 by V3, but here we have find that V3 by V4. Okay, so we can write this term log base E V3 by V4 to the power minus 1. Okay, to the power minus 1, then it will be equal. So T2 by T1 log base E V3 by V4 minus 1 I have written, then log base E V2 by V1, then instead of this V3 by V4, so I can replace it by this V2 by V1. Okay, so finally you will get this value as minus 1. Okay, so if you just implement this minus 1 to this term, so 1 minus T2 by T1 you will get. Okay, that is why I have written in the previous slide that efficiency of this heat engine is equals to 1 minus TH by TL. Okay, or T2 by T1. Okay, if the heat source temperature is T2 and the heat source heat sink temperature is T1, then you can write like T2 by T1. Okay, if it is you are taking TH, then you need to write TH, and if it is TL, then you need to write TL. Okay, so you need to practice actually. Okay, dear students, you need to practice this derivation, then only your things will be clear. Otherwise you may stuck. Okay, if you just want to do it directly in any examination, okay, so you may stuck. So that is why all these things needs to be practiced. Okay, first you should know what is a heat engine. Okay, then what is a Carnot engine. Okay, so Carnot engine is nothing but a heat engine, which is a hypothetical engine, so where it is where all the processes are reversible. So four reversible processes are there in a Carnot engine, and it is the most efficient engine, but the efficiency is not 100%. You need to remember that one, but it is having maximum efficiency. Okay, and it uses ideal gas as its working fluid. Understood? So I will be sharing this video in the Google Classroom, and yes, one thing it is left. So we will be meeting at 3:45. Okay, for 15 minutes I will take the class, then our this one topic will be over. Okay, so you just take your lunch, okay, and you just come back for your regular classes, and we will meet at 3:45. So if you are having any doubt, you can ask, and if you are not having any doubt, you can leave the meeting. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.